Saber and Hamid. Saber and Hamid are co-founders of a consultancy called Organic Navigation, where they help customers add intelligence to physical systems. So you get the physical systems, throw in intelligence, and then you get organic systems. That's where, you know, the name of the consultancy comes from, Organic Navigation. Hamid has a PhD in aerospace engineering, and he's an expert in machine learning, time series analysis, and sensor fusion. Saber has a PhD in mechanical engineering, and with expertise in sensor fusion, navigation systems, and custom engineering software tools. So I know Saber through the company that I work for. He used to work for that company before he moved on to start Organic Navigation with Hamid. One other thing I want to bring to your attention this evening is Saber and Hamid run 2 free awesome workshops every couple months. The first workshop is extracting insights from data using machine learning. This is a really good introductory workshop for anyone whose work generates data and they want to pull insights from that data. I mean, so it almost seems like just the intuitive logical step. You're creating a lot of data. You want to get smart. You want to get insights out of it. So this free workshop is coming up on March 4th. And if you can make the March 4th date, they have a couple dates, you know, staggered out months out from that date. The other workshop is called Getting Started with Python for Data Analysis. So Hamid and Saber provide the data sets to use during that workshop, and then you can keep that data set and use it to explore further after the workshop. And so that workshop is coming up on April 14th. So these are free workshops. I'll be sharing some links in the chat for you to sign up should this interest you. One other thing that Saber and Hamid informed us is they're okay with taking questions as they present. So please feel free to ask away, and don't be hesitant to get super technical. These guys are super technical, so we're in good company tonight. So feel free to ask away. All right, so without much further ado, I'd like to present Saber and Hamid. Gentlemen, take it away.
Thank you very much, Eric. And thanks for the introduction. So as Eric mentioned, today we're gonna talk about some of the considerations that we have come across throughout the years applying machine learning to applications beyond just the textbook and the you know, the examples that are usually put into tutorials and things like that. And so let's get it started. Eric, thanks again for the introduction. Very briefly about the company. We were founded in 2016, and we're based in the Twin Cities. And basically, our expertise is applying machine learning or other algorithms, including sensor fusion, and working with the data that is coming off of sensors, and tackling these problems in physical systems. So you can think of, again, like this could be even moving objects like vehicles and things like that, or manufacturing, or like reactors, or all the other systems that are out there. Our background is basically a mix between electrical engineering, mechanical, and aerospace. And basically what we're passionate about is applying sensor fusion and machine learning techniques to problems that have some physics attached to it. And tonight, so we're going to talk about basically start with a quick introduction to ML pipeline. So for the folks who are newer to this area, this should be helpful. And after that, basically what we're going to do is to go over that pipeline and take a deeper dive into what that is. So that the ML pipeline is very popular, and then like it's there's not much new when we're gonna review the material, but we're gonna zoom in and look into some of the practical considerations that could be helpful implementing the pipeline. And at the end, you will have Q&A, but as Eric mentioned, if you have any questions throughout the talk, feel free to jump in. And just to make it more interactive, and it's a Thursday evening, and for sure, thanks again for joining us tonight. But we have made an interactive poll, so we are going to be asking questions and would like to get your feedback as we're going to be going through the presentation. These polls would be related to some of the toy examples that we have put together, and again, just trying to make this more interactive. So here's the link to the poll website. So feel free to enter this into your browser. Maybe I give it, like maybe a minute or so, so that you guys can enter this into a browser, and this should take you to the um, poll website that we have put together. And then as we go through this workshop, and then we're going to have a poll just coming up, um, we can take a look at the results live as well. So I just give it maybe um, a minute for folks to get to this page. And if you have any trouble, let us know. So on the poll, there's also a Q&A. So feel free to use that if you have any questions about the talk. And again, like first of all, feel free to just speak up if you have any questions. But if you want to also post it, you can also post it here. And we're going to also use the Zoom chat if, again, there you have any questions about the logistics and any potential audio issues or things like that. But um, so I think I'm just gonna pause, give it maybe a few more seconds, and let's go to our first poll. So as I said, like we're gonna do a quick introduction to ML pipeline. So it's gonna be helpful for us to know what's your level of experience with machine learning. So now you should see that poll showing up on the web page, and we'll appreciate your feedback. It helps us to know, how much time we could spend on the basics. We don't want to do a repeat if that's a that's a known topic to the majority of the folks.
Answers are coming in, which is great. Maybe 3 more seconds. All right, I think it's settled.
Perfect. So, okay, it's great. So we have a mix here. So like we would try to cover some of the basics and go through those. And again, even on those, feel free to ask questions. And then hopefully for the folks who have already experience and or are practicing, um, hopefully they would also find something interesting that they can use on their day-to-day projects. Now, moving on. So what is machine learning? You know, uh, there are different terminologies out there. There is artificial intelligence, machine learning, and deep learning. And we find it, maybe useful just to, at least from one point of view, make the distinctions at the beginning. So basically, machine learning is a subset of artificial intelligence, and it's just a way of realizing AI. And the main idea with machine learning is that you know if we give data to like the machine learning algorithms, they should just be able to extract insights or behave in a smarter way, or basically start learning from the data that we give to them. And I like this chart basically because it shows how things progressed in this area. And it also shows how they're subset of each other. But with artificial intelligence, mainly it's any machine that starts, behaving like a intelligent system. And it can be just bunch of if statements that you put into a machine. And honestly, that's how it started. Like all these earlier applications of artificial intelligence were about like how to play computer games. And usually on the back end or on the computer sides, these were implemented through a bunch of if statements. So like someone who had the expertise about that game sat down, and then they said, like these are the rules that if the computer follows them, they're going to be winning or playing smarter. And later on they were thinking that like if you just give them the data about like how they how two players maybe interact, these algorithms just start learning from that. Maybe we can leverage that data. And then there were all the applications about like um, how to detect emails that are spam, and like doing voice recognition. And later on there was deep learning. So maybe about 10 years ago, that's where and deep learning is basically just a realization of machine learning. It's a set of algorithms that basically leverage neural networks, and they started to become very popular because suddenly the computational power was available. So the whole neural network wasn't new, but the computational power started to become more available, and people have started using those. So this is at a high level where like machine learning would sit. And in general, with ML problems, you can divide them into three categories. There's basically supervised learning, where in supervised learning, the inputs and outputs are basically clear and defined. And the goal would be to basically have the algorithm learn from pairs of inputs and outputs. Now, the type of problems that again sit under supervised learning are regression and classification. And this diagram on the right basically shows how a supervised learning would look like. So basically we have a set of images, and then we also have, you can see by each image, we have a label. So in this case, we have duck or not a duck. And the inputs would be the image, and the labels are basically the labels that someone has assigned to these images. And now we give these pairs. So you can see again, the pair of image, the pair of the label, we give them to the supervised learning algorithms, and then we create a predictive model. Once the model has been trained, now we can give it a new image and be able to get the label from it. Now there is unsupervised learning, and in the unsupervised learning, basically we don't have the input-output pair. Basically, we have the inputs, and then we want to basically either put them into clusters or start gaining information about how they look like, identify patterns. So there isn't necessarily like a label attached to it. And again, in this case, it will be the example of like, having all these images and being able to put them into different categories. And there's also reinforcement learning, again, a topic that, again, maybe more recently has gained a lot of attention, especially in academia. And this is basically learning how to interact with the world based on the feedbacks that you receive. Um, and maybe if I want to give an example here to make what reinforcement learning is more clear, you can think of the case where you are a salesperson and then you have maybe, let's say that you have 5 products and you want to start selling those 5 products, but every day you have limited resources, you have limited time to start advertising those. So without any information up front, you basically decide to pick a product and go out, and maybe these days virtually go out and start like advertising that product and show it to other folks and tell about the features. And at the end of the day, you come back and then you would have some success, right? Maybe you have sold you know 20% of the products you got out there, and then maybe you made some like revenue from what you have done. The question is that like the next day I still have 4 products. I tried one product. What should I try the next day? Should I already go with the product that I already tried? I roughly know, I'm going to be this successful with it the next day. Maybe I can do better. But you always think that, should I go with a new product? Well, the risk is that if I go with a new product and then it's not that popular out there, I'm going to have like a smaller revenue. But if I go with the product, which is, potentially could be more popular out there, and then that's basically the reward part of it, maybe I would become more successful than today. So that basically, and then you take again, like you take a, maybe you decide to take both out, maybe like half of a day I would try one, and then the other half I would try a new product. So all those put together would form like a reinforcement learning, where you're trying to actively learn from the feedback that you receive from the outside, and make your decisions smarter and better towards like a target, which in this case was like making bigger revenues. Now moving on, um, thinking about the machine learning process, and this is a diagram where significantly simplifies things, just to know what are the steps at a high level included here. So the steps are basically, we have divided into like development phase and deployment phase. And in the development phase, usually it starts with a hypothesis plus data. So, you have usually like a hypothesis that, like, can I use my input or this type of, like features that I have to make a prediction about something. So you have a hypothesis and you should have data. And right away, you can see that without a hypothesis or without a data, this thing won't get started. So like a requirement right off the bat for machine learning um, process is having the data plus the hypothesis, obviously. After that, you start training a model. You would train your models and you get your trained model and you would deploy it. And the deployment could happen on like a local instance, or it could be on an embedded processor, or it could be on the cloud. So these days you have a lot of options. And now you would push new data to it and get predictions. In this talk, we're going to focus mainly on the development. We're not going to discuss the details and the some of the fun things that can happen when you take machine learning out to real life projects on the deployment side, but we're going to mainly focus on the development and early stage development of these machine learning tools. Now, in the next set of slides, we're going to first focus on the hypothesis and see what type of hypotheses are good to be used for machine learning, and then talk a little bit about the data, and then take a deeper dive into how we should train a model. So moving forward, the first question is that, is machine learning the right tool? And I want to start by a quote from a former colleague, Rich, uh, which I really like. He used to say, and we were like in this AI lab, and he used to say, not all problems are a machine learning problem. And I specifically like this because, when you're in the mindset, either, like being a data scientist or having heard about machine learning, you would constantly think about like, can I apply this? Where can I apply this machine learning? And most of the problems you hear about, you would look at them with the mindset of like, let's apply machine learning to this problem. But, changing that attitude is that like, hey, I have a problem. Is machine learning the right tool here? And basically, we need a hypothesis that would fit with the ML framework, and more importantly, its limitations. And then we are going to talk a little bit about its limitations. But it's also important to know the limitations of any tool that we are going to use. So basically, the bottom line is that machine learning is a hammer, and it's a very powerful one. But again, it's one of the tools in our toolbox, and then it's one of the options that we can go after for solving our problems. And the other important thing is that, as we said at the beginning, machine learning models, they learn from the trends in the data and not necessarily the underlying physics. So whatever data that you give them, that's the extent that they're going to be learning from. So that's why the data and the quality of the data that we're going to give to these algorithms is super important. The underlying physics, that's not something that they can easily even leverage. Excuse me. And now, because they learn from the data that you give them, they only can find a local solution to the problem you have. So they're not going to find like a global solution for the problem. So the limitation, or like the basically the outcome of this is that, let's say that you give them a set of data and then you find a solution, then you give them another set of data. The solution from those two data sets will not necessarily be the same. This even gets more complicated when you start working with more and more complex machine learning methods, like the convolutional neural networks with a lot of layers. Some of them have like millions of parameters involved, and like you have to make sure that the data set you give them would give you the solution you want, and then be also aware that if you give them a different data set, maybe with a different distribution, you might end up in a different point. And finally, and maybe more importantly, is that at least so far, how ML models make a decision differs from humans. Like the way we make a decision, again, like maybe watching kids grow, you can see that again, they take a lot of information into account, even as we do our daily jobs. We drive, we go shopping, we pick items, we interact. The way we again make decisions here, uh, they're not the same way as an ML model would make decision. At least again, not yet. And we might be there in 10 years or 20 years, and there've been good progress towards that effect. But again, we are not there. But the important thing is that they do make a decision. So they won't just stop and look at you. If you give them an input, they're gonna make a decision. And this is very important, especially once you start talking about machine learning and how they're gonna be applied in physical systems. This becomes very important because you should know that your machine learning would make a decision. So to make like to basically go through this example and basically show you more where these things would become more important, we have put together like two use cases that we're going to discuss, and these are going to be about like the suitability of using machine learning for the applications. So let's talk about adversarial attacks. So adversarial attacks are basically when you have developed a machine learning model. So let's say that I have developed a machine learning model from a data to perform a task. And now someone would try to intentionally design inputs that would make the model that we have trained make mistakes. So, like they're going to be handcrafted, inputs that are going to make the machine learning model, you know, have a mistake. And here's another poll coming up. Again, if you recently joined, feel free to go to this link to participate. But the question is that like these two images, they're basically one of them has been perturbed a priori, and then it was classified as a parking meter. So the question is that left or right?
All right, answers are slowly coming in, maybe another 5 seconds. And maybe after this poll, there's a relevant question about training data and images versus sensor data. Maybe we could bring that
Sure.
up after this.
Yeah, let's get that too.
All right, I think we're converging to an answer.
Okay, perfect. So yeah, like I think this is perfectly like you know, everything's equal, right? We have 17% left, 17% right, and a lot of folks are not sure. And like this perfectly makes sense. So let's go and take a look. So the image on the right was detected as basically a parking meter. How and why? It's really hard to see. What the authors did in this case was that they added a little bit of noise to the image on the right. So it's really hard to see. What if you really focus or zoom in, and you would see that like maybe on the face of this dog there's some noise added, but it's really really minimal. Like even when I look at this, sometimes you're like fighting against the dust on your monitor, and you're like, is this the image or is this my monitor? Like, but it's like to us human beings, these images look identical. So I think it's really hard to find anyone who would take a look into the image on the right and then call it like a parking meter, right? So this is where we are saying that the way that machine learning models make a decision differ a ton, or at least again so far, it differs from how human beings make a decision. Um, Now, let's maybe wrap up the example about adversarial attacks. So, in this case, like you would say that, it's no big deal, right? I mean, we have a dog which was detected as a parking meter, like no big deal, it's not a big issue. That's true, like when we are dealing with image classification in this setting, maybe it's not a big deal. The problem comes up when this gets into more serious applications. So the same research was done on, or a similar research was done on the traffic signs. And in this case, this was like a targeted attack. So what a targeted attack is that it's basically when you try to, not only perturb the input to make the machine learning have a mistake, but basically you're targeting for a specific mistake. So in this case, the authors try to make these signs all be classified as a speed limit of 45, and look at their success rate. Like in this case, with a few patches of like making a slightly the sign darker, they were like 100% successful. And they have a pretty good success rate here in making all these signs look like a speed limit of 45 across a lot of different range of distances and angles, which we have summarized only like two of those cases. And again, more interestingly, in this case, this is like another research lab, or basically from a company that they also work on autonomous driving. What they did in this case is that they took like a Tesla autonomous driving system, and then they were able to fool that system by like seeing a lane on the left side here by only putting two small stickers. I think two or three. They might be three. I think one before what is shown in this image. But by just putting two or three small stickers on the left side of the Tesla autonomous driving system, they made the system see it as a full lane. And when they have a video of showing like the autonomous driving vehicle taking action based on the lane, and like it was driving towards the lane. Feel free to check out their report, and also they have a video showing like how this thing has happened. So this is again like you know uh, the robustness, and especially like you have developed a machine learning model. It makes good predictions in the lab with the data that you have generated. But again, there is this limitations to it, which needs to be studied. And not to say that, again, there isn't a fix here, but again, you should be aware of the limitations of the model. Should we pause, Hamid, here and maybe get to the question?
Questions, sure. Yeah. So Evan brought up a good question relating to training data and images. So he says that a lot of the ML model works, and a lot of the examples that are based on image data, but the things he's working on are sensor measurements, and they're not easily visualized.
Mm-hmm.
So how do you filter, clean, visualize these sensor measurements, and make sure your training data set is representative of any interference, and not other pieces that you don't care about, not full of junk? And I'm not sure what the difference is between the interference um, and outliers, but maybe a bit on filtering and visualizing and cleaning sensor data.
Yeah, very, very good question. So, like we also deal a lot with the measurements from the sensors and applying techniques on those. And yeah, it's not super straightforward to start visualizing that data. Um, Usually the way that we have been working with it is that we alternate between the time domain and frequency domain when it gets to visualization, and each would have its pros and cons. Even like the good thing about frequency domain is that like you can compress kind of your long time or long time series into like a smaller chunk, and then visualize it and look into the modes that it has. The other way of looking at it is maybe a mix between the two, is to look into the spectrogram, where you take like a small window and then you apply like FFT on that window, but you keep rolling that window over time. So, like that, then it will show you if you have, like if you have a trend or like a mode that is changing over time, that kind of helps you visualize it.
Mhm.
Things get more interesting when you have multiple sensors. Like once you have multiple sensors, it's really hard to start visualizing them and making sense of them. But the way we have usually been, trying to at least tackle it, right on the top of my head, has been both switching between a time domain and like frequency domain, and also looking at the hybrid approach like a spectrogram, where you swap the window over time to understand your data. And then there should be more coming up on that,
Mhm.
not on the visualization, but just on the requirements when especially it gets to the sensor data. So hope that, I know it wasn't the perfect answer, but like if you have any follow-up questions, let us know. So getting back to the the whole problem of like, is machine learning the right tool here? Let's look at another example. So unfortunately, there was like a fatal accident with the Uber self-driving car in 2018. And this accident basically involved like a pedestrian crossing the street at not an intersection or not a crosswalk. And as they were crossing the street, the Uber's self-driving car didn't take the right action. So the pedestrian didn't see the car didn't see the pedestrian, and unfortunately, this crash happened. And basically, it was a fatal crash, unfortunately. Now, several factors played into like played a role in this crash, and the results that or the text basically we're showing here are all from the reports that were published by NTSB, and then we have the link on the presentation too. They have a lot of documentation on it, and then we have tried to basically summarize it, and so that this information can be also found on this link. And several factors played a role. So, the first thing is that the vehicle operators had a prolonged visual distraction. So they were basically watching a TV show on their cell phone. And the vehicle had an operator, and then the operator was supposed to take control of the vehicle in case of emergencies. But they were not paying attention to the road basically at the time of the crash. The pedestrian was also doing had kind of like an unsafe behavior, right? I mean, they were crossing the street at night at a location which wasn't a crosswalk. And now getting to the manufacturer, basically, the vehicle was a Volvo, and it already had like a forward collision warning system, but that system was leveraging some radars, and Uber's system had its own radars, and they thought that the radars might interfere with each other, so they disabled the Volvo forward collision warning system. So these are all the factors, but you get to this one, which says the system's inability in this crash to correctly classify and predict the path of the pedestrian crossing the road mid-block. And this is where, it starts to catch your attention kind of, like, why would the system be, like not able to um, classify and predict the path, especially again, like maybe for us who are more on the technical side, you would think, like what happened really under the hood that the system wasn't able to detect this crash. Now, with all these self-driving cars, and here's another survey coming up, we know they have sensors on them. So this survey is basically, like, what do you guys think? Like how many sensors was the automated driving system leveraging in this case? So the poll question should show up. Let
Yep,
us
and
know what you think.
the answers are rolling in here. Another 5 seconds. Maybe if someone has a self-driving car, a Tesla, they can go out and count quickly. All right, things we've converged here.
Nice. Yeah. So like, yes, it was using 20 plus sensors. And um, let's go to more details here. The self-driving car, these are all the sensors that were mounted on that car. And like from a technical point of view, it's first fascinating to see all these sensors on a car. Even like as engineers, we were like, oh, all the sensors that I can start working with. But just to mention a few, there was this 360 lidar. There were 8 radars mounted to look front, back, and also on the sides of the vehicle. And then there were several cameras, both near field and far field to, like detect the lanes and things like that. And then there were also like ultrasonic sensors. And on top of all the sensors showed in this diagram, there was also IMU and GPS being leveraged by the system. So again, like from a technical point of view, you see like, we have pretty much all the modalities of, you know, detecting objects on this vehicle. We have radar, we have lidar, we have camera. It would be like, how come the system didn't see the pedestrian passing the street? We have everything we basically need. Now you look into the report and then you see that, well, the system did see the pedestrian crossing the street. And actually it did see it about 5.6 seconds before the crash. And so the sensors did their job. The sensors did detect the pedestrian crossing the street, and then you would be like, okay, then what really happened here? What the report says is that the system, yes, did detect, but the way the system was put together was that everything was driven by a classification algorithm. And what that classification algorithm was doing was that it was using the sensors on board to classify an object. So it was detecting an object, and then it was giving them a label, either saying like it's a driver, it's a pedestrian, it's a bike. And like maybe adding to the complexity here, the incident here was basically the pedestrian, they were walking their bike across the street, and then that's why the system kind of was struggling. And what has happened in this case is that that classifier, which was supposed to start this whole you know um, object tracking and figuring out where the objects are, that classifier switched the classification about 7 or 8 times in that duration of 6 seconds. So first it said, it said, well, it's a vehicle. Then a few or fractions of seconds, it changed its decision to saying that, no, it's not a vehicle, it's basically a bike. Then it changed it, no, it's not a bike, it's like other, it's not other, it's a pedestrian. So, like the classification changed several times. What added salt basically to the injury was that the bigger system was resetting the history or the path of the object whenever a new classification was performed. So if they were seeing a vehicle and then they tracked that vehicle, let's say for a fraction of a second, and then they saw it's maybe moving in one direction, the moment they reclassified it, they zeroed basically all the history of the new object that they were detecting. So to the system, these were basically objects that although moved over time, they basically, from the bigger system, they never moved, right? So it was like a vehicle on the side, then it was like a pedestrian on the side, then it was like a bike on the side. So they never saw that path. So compare this where, for example, like hypothetically, the other way of doing this would be like you would track an object and then you would try to assign labels to it about like, this is a bike, this is a vehicle. And then you want to like just reset the tracking history if you make a new decision. And basically resetting this history never showed that this object, whatever it is, it's a vehicle or it's a bike, it never showed that it's coming close or it's coming into the way of the vehicle and like making the necessary um, actions happening on the car until it was very late. So basically, in summary, and this is basically the quote from the report. In summary, again, when we are working with an ML machine learning or like all these techniques that we are relying on our data and things like that, we should also think about the bigger system, where they're going to be used, what are the risks involved with them, what happens if they make a mistake, and be aware of all the limitations that potentially they could have. And interestingly, since this incident, we have seen cases where like I like this wording here. It says a smart application of machine learning. Why this is interesting to me is that machine learning is supposed to bring smart to your systems. Now they're saying, they've started to say you have to be smart about applying machine learning to make your problems smarter or your applications smarter. And this is by Aurora. They're also like another autonomous driving startup. But again, I think that some of these things should be thought through as we are leveraging ML beyond like just tagging or face tagging and things like that into real applications. So now let's move forward. Sorry, go ahead,
Saber,
Hamid.
sorry, yeah, before moving on from the Uber example, um, there's a question about did they correct the issue or with the whole indecision after the incident happened?
So, there were some, very good question. To be honest, we didn't follow up the Uber's action and how their architecture changed over time. The report did mention that Uber has taken action into, because, we mentioned 3 or 4 key factors. I think they did try to address all the 4. I didn't necessarily see what the action was in terms of like the system architecture. I think they might have made it public or not. I saw some actions from Uber on all the 4, especially like regarding, I think the first one was, the operator not paying attention to the road and being distracted by their cell phone. I think they started right there and they were making progress towards the other issues as well.
Mhm, mhm. Just which is kind of non-traditional in some of these safety critical engineering systems where historically you would test it and validate it and get it like certified and not change it until something happened, and then you would have to like prove what changed. But
Mhm.
these are so like constantly evolving, as you mentioned, like the report says, numerous changes have happened to the code base since this incident. So
Mhm.
it is a little
Mhm.
harder to know what the actual implication was, but they certainly made some changes.
Cool. So let's go back to the diagram we had. So here we talked about the hypothesis, like um, basically make sure that the machine learning algorithms are going to use are the right tool for the application and be aware of the limitations that they might have. We'll now talk a little bit about the data, and then we're going to jump into model training. So the data, basically, the data we collect should be representative of the target problem. This seems a bit obvious, but basically, what this is saying is that don't use the data from like a lab experiment or multiple lab experiments and then expect this model that you develop work in the wild. So like if you are going to be testing this model like in Minnesota winter, make sure that you have some data from Minnesota winter, not only from like a device point of view, making sure that your device works, but also from the fact that this is just different environment and the signals you're going to get are going to be different. And for example, if your use case has outliers, let's say, we talked about sensors and, the difficulty they have about visualization, but, like working with the sensors, you would know that another difficulty with them is that occasionally you're going to have outliers. So outliers are expected. And we shouldn't just sit down and try to clear those outliers from our data before feeding it through the machine learning models. Let those outliers be in, and we have to just try to reject them. Have methods to deal with those outliers robustly, and then we have that as part of our testing mechanism. When you're covering, or when you're collecting data, make sure that like you cover all the use cases. For example, if working with images, make sure that like you have the all the lightings that are going to be possible. If it's indoors, like there would be limitations on the lighting and different scenarios. If it's outdoors, is it night, is it day, is the camera facing the sun or the light, all those things are important. The angle that you take an image, the distance to the object would play a role. And if working with sensors and IoT, again, as I mentioned, like the environment would play a role. Again, we're not talking about like the sensors surviving in the cold or in the heat. This is more like when you are having your system out in a different environment or weather condition, those would play a role in the data that you're going to receive. For example, the biases of your sensors might change due to temperature. Similar with vibration. Let's say that I have a machine, I put sensors on it, and I take it to my lab and everything works great. Then I take that machine and put it into the manufacturing line. Well, there are other things vibrating. It's not my machine by itself in the lab anymore. It has all these other machines running side by side, and there might be vibrations coming to my sensors, and then it's gonna impact the data that I've been having my machine learning model train on, or even modes of operation. Um, uh, like if I get my machine in another location, it might have different modes of operation suddenly. It might be reacting to the temperatures and those other things and creating new modes of operation. And again, for sure, there are going to be more examples in each use case. Now, this diagram at a high level shows the machine learning process. And this is the standard machine learning process with, again, like you would see this with any pretty much training on machine learning. There might be a few tweaks here and there, but let's go through this. And this is the part that once we go through this once, in the next set of slides, we're going to dig deeper and then talk about each part of this diagram. But on we get the data basically, which we talked about. It's some of its requirements. Then we split it into three sets. There's the training, validation, and test. We take the training data and we pre-process it, which could include like normalization, maybe generating new features, or pretty much anything that is needed. And we develop a model. Then we are going to use the validation data to tune our model. Like we're going to improve it, see if we can use other models. Maybe we should, like apply different techniques to it. And then we also use it to do error analysis. Again, like we're going to talk a little bit about both of those, both model tuning and error analysis. But that's where we're going to be leveraging our validation data. Once the model has been finalized, we're going to take our test data and make a final evaluation on the model. This is the evaluation that we do to get like a metric of interest and report it, and then be like, hey, this model is good, to this much, or that's where we would do the final evaluation. So again, this is a very standard high-level machine learning pipeline. Now let's just start digging in, starting with splitting the data. So as I said, it's basically the process of dividing the data set into three splits: training, validation, and test. A few notes here. So first of all, make sure that you have similar distribution between these sets. And this is kind of maybe even back again to the visualization question we had on the sensors. That's going to be a bit more difficult. So when you are splitting your data, whether you have images or sensor data, make sure that you have the same type of data in each bucket of sets that you have created. Then use your training and validation set for development. So when you're developing a model, you're iterating over models, use your training and validation set. I would say, first of all, spend time understanding your data and, like visualize it. Look into the different column of, sensor that you have. Look into different images. Look into the means, standard deviations, outliers. Just spend some time understanding the data. Check if your data is imbalanced or biased. This is also very important. You guys might have heard about like bias in machine learning and the data sets. And like the I would say the more obvious ones are like the gender bias, or there's also like the race bias. So like, so those are some of the more obvious cases, I would say. But the bias in data set can go beyond that. um, just to iterate back, we talked about the case where the Tesla self-driving car detected three stickers on the road as a lane marking. Well, they suddenly didn't jump to that case. The people who were working or researching that to try to find cases where the Tesla lane detection system would fail, they started by creating or adding noise to existing lanes. So they were picking up like a portion of the lane and then they started adding noise to it, so that they wanted to see if the Tesla system won't be able to detect that lane. So they completely started on the opposite side. They started adding noise and added noise and added noise, and then they saw, Tesla is really performing well. No matter how much noise they add to these lanes, they make them thick, they add patches, they start behaving very well. And then that's where they thought, well, maybe they're biased to, all these different lane cases. And then they have had a lot of abnormal cases and very robust. Would that mean that they're more sensitive now? And then they would pretty much pick event three stickers or like configurations like that as a lane. So then they changed the target from like making Tesla fail to detect the lane. They were trying to make Tesla pick a lane which wasn't a lane to a human being. And they were successful. So in this case, again, like I would call this maybe a non or a less obvious bias, but when Tesla engineers were generating or collecting this data, they were mainly focused on the anomalous cases, like let's make it noisy, let's maybe make it thicker, maybe thinner, put a snow and things like that. And that's how they collected data set. Now the whole algorithm was more sensitive in picking up lanes, and it just picked up like three stickers on the road as a lane. And you might have heard about cross validation. Again, make sure that you do cross validation on these two sets. Like we want to keep the test set untouched until the end. And summarizing that is like, do not iterate models on the test set. But once you deploy this model out, and then again, we're not going to talk too much about deployment, then that's where you would get fresh new data. And then, like before, iterating on it, you can use that new data and update your test set. And either you can put some of that back into your validation, or again, keep updating your test set with the new cases that are coming in. Now let's take a look at an example here. In just a heads up, there's going to be a survey coming up soon, so pay attention. But basically, this is a toy problem, and then we're going to talk about like splitting the data. So what has happened is that like we have had, earlier on in the COVID, maybe everyone's home, and then we're thinking about like, what should we do? And then we think about like, doing activity recognition using 60-second intervals of sensor data. Let's say that we want to use the like a smartwatch, and it has like an accelerometer on it, and then we want to use that data to detect what someone is doing. Are they stationary, are they walking, or are they running? With the bigger goal of like promoting like, hey, you should go out and do some exercise. But that's the goal. And then we have the smartwatch, and again, I know this idea is out there. Let's just pretend this is really, really novel. But we collect that data, and then we ask our friends. We ask 4 of our friends to send us sample. Again, this is just an example, like think of it as like we collect data from a bigger set of people. We kind of run out of shapes here and limit it to the four friends. And what we're going to do is that we have asked each friend that we have had to basically collect a 60-second interval of the activity, and either us or them, they labeled it too. So here, like the S would mean that this sample has been like a sensor signal which has been stationary. We have another sample here which has been the person providing the data be walking and then running. So this is a data set. And again, like we have four, again, just visually showing four. Think of it as, they have more cases, but this is the four that we have collected data from. And going through the machine learning pipeline, we know that the first thing we should do is to split the data. So we go after it. So we know we split the data, we have our training, validation, and test set, and things look great. Here's a survey question. So we randomly split the data. Looking at the split that is shown here, either looks good, let's continue, or, well, not so fast. So the survey should come up.
Yeah, this one will take a little more thought. So let's give it like 20 seconds here. Maybe 10 more seconds. All right, we almost have 10 people, so I think we're
Okay,
good.
cool. So let's see the results. Perfect. So we have, and like the majority is saying, well, not so fast. And that's the right answer. So let's see why. So the way we split the data is, again, like just as a recap, I'm showing it again. Um, and originally going back to the original data set we had from the four people, we saw people are not running, and then, like you won't be running all day, right? I mean, usually you would be sitting, being stationary, maybe you do some walking throughout the day, but the majority of your time, and remember this was post-COVID, so a lot of stationary, but then, occasionally people also go out and run. So overall, the ratio of the samples we had in terms of running was much smaller than the ratio of just being stationary. In this case, we randomly split data, see what happened. Like we have a lot of running, at least ratio-wise. We have 3 cases of just running sitting in our test set compared with the other sets, which the ratio of running to the other samples are much smaller. So we violated the first point that we talked about, like making sure that they're going to have the same distribution. Why does this matter? Think of it this case. Running, working with accelerometers, you might know that, like when you start moving, your signals are very distinct. You would clearly see someone not moving from someone moving. So possibly running has a better performance when you're developing this classification algorithm compared with being stationary or just walking. Now, you get a performance when you're working on your validation set. And once you go to your test set, what's going to happen is that because you have a lot of running cases, your test performance is going to be exaggerated because, the ratio is not proper. You're not going to have like 3 out of 8 cases or, like that ratio of samples when you're testing this algorithm. So what you need to do is to make sure that you have the right ratios. And again, visually, you have, this is trying to communicate that, like the ratio of samples that we have in this case, running and walking, kind of now match across the training and validation and test set. Okay, so, so far so good, right? We have the same distribution across these sets. That's good. What we do next is that we develop a model. So, we passed the first um, portion of, or the part of the ML pipeline. We split the data, then we go ahead and develop a model. We develop a model, we launch it, everyone loves it. Our friends are really, really smiling because they love it. And then the word gets out there, like then someone new hears about this, and then they say, well, we want to join the program. Okay, here's another survey. Should we be worried? So again, the model has launched. The 4 friends who we get the initial data from, they love the product. They told their friends about it, and they now want to join the program. So we have new users coming in. Should we just relax or should we be worried?
All right, still coming in here. Maybe 5 more seconds. Okay, we're almost at 10. Let's go ahead.
Perfect. So yes, we should be worried. That's the right answer. Why should we be worried? In our second attempt, the way you were testing this, both in the validation set and also in the test set, let's say that I wanted to look into my diamond-shaped friend. I mean, I don't have a friend which is diamond-shaped, but like uh, I'm in that case, we're taking a look at in the validation set from the data set of this friend, but we have already seen some samples from that friend in the training. Looking at the friend who, like the sphere friend, we have also seen some of their samples in the training. When we go to the test set, that's the same case. Like we have again the squared friend, and then we have seen some of their examples both in validation and training. So the friends who have loved this product and they have been providing positive feedback are the people who we have seen their data, who we have seen their samples in our training set. There's going to be always new ones or new people coming and using their algorithm, and then we can avoid it, right? I mean, if you're running this successfully, we should have new users. We can't avoid it. What we can do is to form or split our data in a way that we can at least simulate a case where a new user comes in. So here's our third attempt at splitting the data. What we're going to do now is that we are going to keep one of our friends, the data we get from them, completely unseen in the validation and training. And in this case, the square samples, we are not going to see them in validation and training. So there aren't any samples of those here. And once it's talking about the validation, the diamond samples, they haven't been seen in training. So think of this where, like again, it's beyond only the 4. We have like 20, 30, 100 people that have signed up. We have collected their data. This could even be easily extendable to other systems, images. But the whole point here is that like splitting the data, it's not just that, we get all our data set and we randomly split it into sets. We need to be more strategic about doing this and think about the bigger picture and the limitations of the problem. So again, as you have seen the trend being is that adding some um, considerations for you guys, especially taking this into real applications. And at least in this case, we can simulate and see how the algorithm would do, pretending that someone who we haven't seen their data joins the program.
Just a comment Evan threw in here is that this exact example is something he's seen in practice, and the solution they came up with was the solution that this example shows.
Nice. Okay, so shuffling the data before splitting. Again, going through a lot of the tutorials, blogs, trainings. A key step before splitting the data into training, validation, and test is to shuffle the data. And um, here we have a question. We haven't put a survey for it. And this is kind of a homework. So the question is that, or the statement is, we should always shuffle the data before splitting. And the 2 options are true and false. Feel free to think about this. Again, we're not going to talk about it. But if you were interested, we can maybe discuss it later at the end. But again, maybe you can sense the tone that, hey, all the time you should be shuffling data. This could allude to, this shouldn't be the case in some scenarios. Okay, let's talk about the next step, normalization. Again, pretty standard, like transforming input data or features that we have to be of similar scale. That's what normalization is. Sometimes folks scale them by min and max, and sometimes they scale them by the standard deviation. Kind of similar, but like we kind of make sure that all of our inputs and features have the same size. And again, very standard step in pretty much all the machine learning material. And now here's an interesting survey question. Which one is true? With normalization applied, model outcome always improves, may improve or stay unchanged, may improve, stay unchanged, or degrade. So the survey should be up. Feel free to think about it. I think the questions are getting a little bit deeper. So again, you know, feel free to spend some time thinking about this.
Maybe another 5 seconds. Questions are getting deeper and the night is getting later. All right, I think we're beyond 10.
Perfect. So great again, like we have the right answer. It may improve, stay unchanged, or degrade. This could be a bit surprising, like in terms of like, especially thinking about the degrade, like how come normalization could impact the performance, not in a good way. But let's see this through an example. And, I'm hoping that the examples at least get more exciting, as we go through the presentation. Um, but in this case, we have a toy problem. So we have this reactor, which Eric might like. In this case, we have a reactor, and then we want to monitor basically the modes of this reactor, and then we put two temperature sensors. We put one up here, and then we put down maybe inside or on the side. It doesn't really matter. This is just a toy problem. But we put two temperature sensors, and then we start collecting samples about the temperature. And once I visualize it, looking at it, like, if we have like an expert take a look at this, they would see that, well, this reactor seems to have two modes. Like there's one mode where, the T1 is around 70 or 80, and then there's another mode, which is 110 to 120. Well, like we do see two modes. This is just an example. When we have, again, like in real cases, it's not just the two sensors that we can easily visualize. There's going to be a lot more sensors. But just the two here would help us understand the issues that could be there with normalization. So now what we do, let's pretend that we couldn't visualize this data. We give this data to like a clustering algorithm to cluster these data into the modes that are existing in the data. Here are the results. So we took the same cluster and then we applied it to the data without normalization on the left and with normalization on the right. The results are interesting. On the left side, where we didn't normalize the data, we see the two modes that we were expecting, like the engineers told us that, like, yeah, there should be two modes. Now with normalization though, we see four clusters getting formed. Why is the reason? So what happened is that once we normalized T2, suddenly the impact or the range that T2 had is now very comparable to T1. So when the cluster looks into the data here, they would see the same extreme or the same range of data for T2. So what basically happened is that now the effect of T2 has been exaggerated for the cluster without the cluster even knowing. Now, in summary, normalization can improve outcomes, but it can exaggerate the influence of the inputs. The good thing is that not all the algorithms are sensitive to normalization. For example, decision trees are much less sensitive to normalizing the data compared with, like, for example, neural networks, or some of the, especially clusterings. Clusterings are usually very sensitive to how you normalize the data, but some are not. But again, we just wanted to depict a case where, going through the steps of machine learning, follow them, but make sure that you spend time on each step, making sure that it's the right step for the problem that you're working with. Now, another homework is that should we normalize the output? So in this case, we just talked about normalizing the input, but now the question, again, as a homework, or like we can discuss at the end if there was time, is that should we also normalize the output? Are there any benefits or not? Let's move on and talk about metrics. So metrics are obvious, right? I mean, they're used to measure the model performance. So when we're talking about classification, or a multi-class classification or binary classification, we're talking about accuracy, precision, confusion metrics, Fana score, recall, all these metrics. Or if you're working with like regression, we're talking about like root mean squared error, maximum absolute error, or sorry, the maximum error, the mean absolute error. Those are the metrics that we work with. Now, let's look into the toy example, understanding the metrics and the importance of metrics slightly more. So we have a project, we have this wind farm, and we start installing sensors on these wind turbines, and they start sending the data. And the data they send, we have some experts, some engineers, they sit down and then they look into the data that has been transferred by these wind turbines, and then they label them. They say normal, abnormal, normal, abnormal, and then they give us the data. Now, as we're developing this machine learning tool, our goal is to do this automatically. So we don't want them to sit down and label these as they come from like these hundreds of turbines out there. They label some for us, and then they expect us to come up with an algorithm to be able to at least give them some classification. Let's say this is normal, or no, this is abnormal. You should take a look at it. So here's the problem with the labels. We start working on this, and our initial results show 90% accuracy. So if I come to you and then be like, well, everything looking great, I have 90% accuracy. What is your reaction? Would you be, great, this is promising, or, well, not so fast? So I'll give a few seconds for the survey. It should show up. I won't be disappointed if you say, well, not so fast. So
oh, seems like no one wants to disappoint you today. Answers came quick here.
Perfect. So right answer again, well, not so fast. Why is that? Let's take a look. So we talked about accuracy, and let's look at the confusion metrics. So this is called the confusion metrics. Here we have the actual labels that we were given. So in this case, there is the normal and abnormal. And then we have the predictions, normal and abnormal. And what accuracy of 100% means is that like all the samples that we were given, we were able to classify them accurately. So in this case, we had 90 normal cases, and then we have, which we classified as normal. Perfect. And then we had 10, we had 10 abnormal cases, which we again classified as abnormal. Perfect, we have 100% accuracy. Now let's take a look at another example. If the classifier isn't able to, in this case, classify 5 of the abnormal cases as abnormal, basically it failed. So in this case, we had 10 perfectly classified as abnormal. In this case, it failed, and it predicted 5 of those abnormal cases as normal. And in this case, we have an accuracy of 95%. Now let's look at the extreme here. So in the extreme case, I don't develop a classifier. I just come and then I label everything as normal. So basically, this is either a dumb classifier or like not classifying at all, labeling everything as normal. What is the accuracy I'm getting? I'm going to be getting 90% accuracy. So what we wanted to emphasize with the example is that accuracy and the metrics you're going to use to quantify the performance of your model are important, especially if you're working with biased data, working with the stakeholders, they would become more and more important. So a single number, which is reported at the end of a lot of the trainings that happens by machine learning, may not be a good representation of the metrics that you might be interested in. You should spend time on understanding what the right metric for the problem you're working with is. And again, like I haven't seen a case where like simple accuracy metric would do the job, unless you can hit 100% all the time, I think. Now let's take a look at another example. We have two models here. Like in case one, this is from the last slide. Again, we missed 5 of these cases, and then we get 95% accuracy, which is the accuracy we get. And in this case, I have a slightly less accuracy. So I only get 93% accuracy. So the accuracy is less. If I only wanted to go by the accuracy, I would have picked the case one model. But the case one model, if you look into it, you can see that it gives you a 50-50 chance in detecting the abnormal cases. Whereas the case tool, although it has less accuracy, it has a 80% chance of picking something which was abnormal as abnormal. Why is this important? Again, go back to the toy example. We have these wind turbines. What happens if I miss this 50% of the time? A wind turbine was behaving abnormal and I couldn't pick it up. 50% of the cases, those cases were failed, and like who knows what's going to happen? There would be potential failure which we couldn't detect. In this case, although I have less accuracy, I'm able to grab those cases 80% of the time. But I was able to get there by sacrificing some of my accuracy or prediction accuracy with the normal cases. So what happened here is that 85%, or sorry, 85 out of 90 cases, I was able to call normal normal, but there were 5 cases where I called normal as abnormal. So in these 5 cases, let's think of this being implemented. What is going to happen is that if I call something abnormal, or the algorithm calls something abnormal, probably we're going to send someone down there, right? They're going to travel, and then these wind turbines aren't like, in the vicinity of a city. They have to usually drive an hour, 2 hours. Maybe they're offshore. You have to, grab the right equipment, and then you go in there, and you do your inspection. And if what the algorithm has called abnormal is actually abnormal, great, you're going to be happy, and then you're going to come back. But you would know that roughly in 5 out of the 13 cases that are going to happen, you're going to go there and then only see the algorithm made a mistake. It was normal, and then I called it abnormal, or the algorithm called it abnormal. So what is the right threshold? It really depends on the problem. You really need to sit down and talk to the stakeholders, be like, you know, what is the cost of calling or a false positive? What is the cost of like a false negative here? And talk those through and come up with the right metrics that now, if you develop multiple algorithms, or if you're doing like hyperparameter tuning and those things, you're going to be optimizing against the right metrics. So let's move on to model training. Um, I would say, like maybe one of the important things when you start looking at the model is that we talked about biased data set, but here, like don't be biased by the hype. Determine what is good for the problem that you're going to be trying to solve. Um, just one example is that CNN is fancy. They're very powerful, but they're not very explainable. Again, there's been some research in that direction, and think folks are making them more explainable, kind of, but it's not an easy thing to get to. Decision trees are maybe less state of the art, um, but they're more explainable. So, if you are going to be working with a case, so let's go back to the wind turbine. If you're going to call something abnormal, maybe if we can add some explanation as why the algorithm called this abnormal, before sending someone down there, they could take a look at it and then be like, oh yeah, I see why you called it abnormal. Or they would look at it and then be like, well, you called this abnormal because of this feature, and we don't really see like a rationale or a physical explanation of why this has been called abnormal, and we think this is labeled incorrectly by the system. So again, think about the problem, the limitations you have, the resources you need to do, the fact that like you would make a mistake, or the algorithm would mislabel something, and based on that, make a decision about the algorithm that you're going to be using. Now, where to start? We would say start with simple models. This even could be like a simple mean. If you're forecasting some sensor in the future, maybe just use the mean of your statistics, or start with something simple. Let's start with linear regression. Why? Because it can give you a quick sense of the problem. And you can also use it as a baseline. Like the next time you develop a model, you're going to be happy, right? I mean, you improve the performance. So it's always good to have a baseline. And only move to complex models as needed. Like, again, if you see the need, if you want to improve performance, do move to more complex models. But remember that simplicity is good, and simple models are generally more robust. And this is back, if you remember, even from a mathematical point of view. Earlier on, we talked about like how machine learning models, they use data to come up with a local solution. And if you talk about optimization, local solutions, or local optima versus like global optima, has some role into why simple models are more robust, basically. Now, the model tuning is the part that where you have trained a model and then you try to now grab a model and optimize its hyperparameters. Like if you have a tree, you want to make it deeper, you want to make it wider, you want to add the estimators. If you have CNNs, you want to add more layers, you want to leverage a state of the art, or even within the layer, you want to initialize it differently. The question that comes up usually when you're in this one is that like, how much time should I spend on model tuning? Time meaning resources, right? So like roughly, usually what we have experienced is that if you're like at 70% or so in terms of whatever metric of your interest, let's say again, like accuracy or RMSE, if you're 70% of where you want it to be, it's really hard to make it 90% by just hyperparameter tuning. So like, I have a decision tree and I increase the number of estimators I have. When I have a random forest, I want to try to make it deeper. It's usually hard to go from 70 to 90. Again, it's possible, but it's not very common. So let's say that you are facing that case. You're like, oh, I'm 70% accurate and I want to improve this. We would recommend, like taking some other approaches. You can collect more data, like go after the cases where your model wasn't able to classify. Let's go back early in the presentation. We talked about running. If I don't have a lot of running, maybe I should ask my friend to run more, like grab those samples and like bake them into the classifier so that I can take those cases. If there are anomalies, gain more insight, or extract the data that has anomalies. Reformulate the problem. you know if you only talk about the accuracy, you might go somewhere. See if you can reformulate the problem. Just an example that even we recently faced is that sometimes you think about the accuracy in a global term. It could be like, well, um, let's go maybe to the wind turbine example. If I'm accurate, you know, uh, throughout the day versus my accuracy through the night, let's say that just, hypothetically plays a role. Maybe during the night shift and waking someone up and then be like, hey, could you go check on this? Maybe they won't be so happy. But if it's during the day, they can consult a colleague before taking an action. Maybe it's less expensive. So maybe we can divide it into like, what is our accuracy, during certain hours, and what is our accuracy during some other time period. This thing could happen also in like regions or zones or geological zones or something like that. And you can, or decide that basically you come up with other ways that you can go after the problem. Leverage the underlying physics. That's the part that we also like. If you're working with the physical systems, it is very likely that you can leverage the underlying physics. Talking about the reactors, maybe you can use some of the dynamics of the reactor to reject the outliers if they're impacting your performance. Feature generation. And the way we use it here is different from how feature generation is done in software. So in software, usually you write a few line of code that would multiply the features, divide them, extract new features from something that you already have. Here, we're mainly talking about like add sensors. If again, going back to the reactor, you add a temperature sensors, maybe dropping like a flow meter somewhere, or maybe add a vibration sensor. So, see what else you can measure to basically help your algorithm. So in a nutshell, hyperparameter is one of the ways to improve the performance, but there are a lot of other ways at a bigger level or at a bigger scale that you can think about improving the performance of your model. Now, moving on, um, error analysis. Honestly, this is one of my favorites across all the machine learning pipeline. And what it's about is that basically you want to understand where and why the models fail. And using that information, you want to determine next steps in algorithm development. I can't emphasize this more, but don't bypass this step. Even if you have 99% accuracy, don't bypass this step. Still go back and take a look into the examples that your model couldn't, predict correctly. Or even if you have a lot of good accuracy, maybe go take a look at those. You have 100% accuracy. Is that something you expected? Or no, you're thinking like, my sensors are noisier than what I think, or my images are noisier. I did expect some of these to be misclassified. Even try to make your model fail. Like if you're not getting, like if 100% accurate, like, well, I wasn't expecting that. Let me make this 98%. Go create samples that, are harder or more challenging and see if your model fails or something fishy is going on. An example that I wanted to provide here, again, now, I think all the previous examples, except earlier on the polls where we were on, toy problems. This is actually like a real example. We just changed the application so that it doesn't look like the original application that this algorithm was developed on. But think of this application as we are a company which makes the belts that go on on a conveyor belt. So we have clients that they make these that they have the systems, and then the system involves a conveyor belt, and then we are the company who make the conveyor belt. Now, what you want to do is to help our customers and basically monitor the belt usage to determine the remaining life. So we have like an expected runtime for these belts, and then we want to determine how far a belt is in its lifetime, and basically send them a belt as a belt is coming to end of its life. What we do is that we put a sensor on the conveyor belt, right? I mean, this is a client, the belt. We can't just like take a look at the switch. We don't have access to that for whatever reason. Let's say that it's maybe a regulated environment, they don't want to share that information right away. The easiest is just to tap in like an IoT device, sending the sensor data to the cloud, and then we are monitoring that, and we know how much the build has been used. So we developed an algorithm here. Like it wasn't performing really bad. It was performing actually well. It could detect when a build was in use or when it wasn't in use. Then we said, okay, let's do error analysis. And there were two really good outcomes out of the error analysis, and that's why we wanted to talk to you guys about this use case. First was that once we looked into these errors that the system was making, interestingly, it was making errors on when the build was not in use. And that was a bit odd. Like usually expect those to be like, flat signals, like not much is changing. But what had happened was that due to the environmental impacts, when we were putting this sensor on a new build that we hadn't seen in our training nor validation set, we were putting it on a new one. What you were saying is that like due to the environment conditions, that baseline signal of a build not working was different from everything we had seen. Again, this was due to the environmental changes, all the vibrations from the machines around it. And the way we, so that was a good, observation. So the way we fixed it, and then we helped the system, was that we created fake baseline. So we created like simulated how this system or the sensor would look like sitting on a belt on an environment. We expect like slowly changing an environment, but we do expect some change, and we do expect some bias changes. So we created synthetic data, feeding that into the model. That certainly improved the performance. So that was the number one good outcome that we had. The second good outcome, which was more exciting, is that we looked at one of the belts, and the algorithm was calling the belt, running, 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 and calling it running. But the reports that we had regarding the actual usage of the belt was contradicting the predictions. Again, that's why it was called an error. So in this case, the classifier called it running, running, and then it stopped calling it running, and it said not running, not running, not running. The reports we had or the labels we had for the belt was running, 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 and then not running. So, it was calling it running for a longer time compared with the classifier. Interestingly, talking with that user, the belt had failed. So the whole conveyor belt failed, uh, a few weeks after the algorithm had stopped calling it working. Looking at the signals, you could even see the conveyor belt acting up as it was getting closer to the end of its, the whole conveyor belt. This wasn't just about the belt failing, this was about the whole conveyor belt failing. And you could see that the signals were acting up as they were getting to the end of life for the whole conveyor belt. And that's why, the algorithm was calling it like, well, you don't look like an active belt. To me, you're not really working. And then that started basically a whole new discussion about like, so far we have been thinking about this like sensor to be used for monitoring the belt usage, but maybe now we can provide extra benefit to the client and be monitoring the behavior of the whole conveyor belt system. And then that started a whole new discussion in a business. So moving on, the key takeaways here. Take ML limitations into consideration. And I think, we have talked about, at the beginning, we talked about a few cases where, while you're developing these models, think of the bigger system. Where would this going to be used, and would any of the ML limitations play a role? If they do, find ways to adjust them, or be ready again for those. And spend time analyzing the data, you know, um, and determining the proper metrics. So with the whole ML pipeline these days specifically, there are a lot of packages out there. If you're talking about Python, there's scikit-learn, and like even ingesting data with pandas, training models, there are all the TensorFlows, all your deep learning models, there are even pre-trained models. R is the same. There's a lot of tools out there. MATLAB has its own things. Cloud has a lot of tools. So honestly, it's very easy to go from like, oh, I have collected my data, pushing it through the pipeline. Well, I have this much accuracy. That process has become very, straightforward, which is great. But do spend time. So even if you do that first path or first pass through your data, step back and take a deeper look into all the steps that are involved and spend time. Again, spend time on analyzing, looking at the metrics, and understand the errors. Like understand why the model fails. Even as I said, make your model fail. Like if you're not seeing a lot of those cases, understand when it will fail, understand the edge cases, collect new data. And I think more importantly, then looping back through all these cases is to stay connected with the subject matter experts and the stakeholders. Stay connected with stakeholders because those are the people who would be keen on the errors or the metrics. They may not be super technical, but again, they care about like how many times they're going to be sending someone checking on a wind turbine. Or they might be, again, like a user of the technology you're developing because they're, for example, working with that conveyor belt. And then stay connected with the subject matter experts. Again, like I could sit down, normalize my data, and suddenly get like 4 modes of operation for my reactor. But then I sit with a subject matter expert and like, how come you got like 4? This thing only has 2 modes, and probably something has going on. Well, thank you guys. This is not a survey, but just wanted to thank you. Here are email addresses, and I think we have some time for questions if there are any. Again, if you have any questions, feel free to reach us, to reach out, and these are our email addresses. Feel free to connect with us on LinkedIn. As Eric mentioned in the beginning, we also have a couple of workshops coming up. So if you go to organicnavigation.com under workshops, I think we have 2 workshops coming up. So feel free to sign up, and let's see if you have any questions.
Saber and Hamid, thank you so much for the presentation. Lots of very good, takeaways from the different projects that your company has done for people to take, nuggets here and there and incorporate into what they're doing. So we'll take questions. Actually, there's a question here from Pavan. Will the deck slide be available?
I think so.
Yeah.
No, we'll get back to you on that. I think how would we share it, Eric? How do you guys have done it in the past?
Yeah, so the way, go ahead, Justin, please.
No, I was going to say we can basically put it out on a shared Google Drive, open public link, and we are recording tonight too, so that will be there. So if anybody wants to rewatch all this video, but yeah, if you guys want to get it over to us, I think we can put it out in a location that would be a shared public link, and then we can send it out to the people that attended this meeting through Meetup.
Sure. We'll be in touch.
Yeah. So questions and comments too. In the past, the way we've done these meetups is sometimes it's more of people wanting to comment rather than questions. They're like, yeah, like for example, I saw in the chat there one person. Let me see who that was. I think it was Evan, about the training data. They did something similar to what you were talking about. Let me see if I can find that in the chat.
Sure, yeah. We would love to also hear about other use cases or similar cases that that folks have had, similar considerations or different ones that they had to deal with. We'd love to hear about those as well.
Yeah, actually, that was Evan. He said the participant episode hole that you were talking about was the solution. So yeah.
I like the diversity of backgrounds too. There was comments about aviation safety and safety critical systems, as well as other sensors and image-based data. So kind of spread the whole breadth of applications.
Mm-hmm. Yeah. Cool. So yeah, going once. I sound like an auctioneer now. Going twice. Yeah. So a comment from Tezi Song. Great presentation. I concur.
Yeah, thank you, guys.
I
Well,
concur.
thanks for joining us this late on a Thursday, and thanks to you, Eric and Justin, for giving us the chance to talk tonight.
Yeah. Thank you for the time. We really appreciate it.